So our last two speakers of the day is Nikos and Mubashir. Nikos came into the project when he was when we transferred here in Venice, and basically he stayed until he was offered a highly rewarding job in the renewable energy sector. So he left us, and that's the sad thing of getting good people, as many of the people who talked to you today, at some point they're going to come to your office, or specifically like Nikos, call you and say, hey, I got a good job offer, I'm not going to say no. And then you're left in that sort of hanging between being happy for them and being sorry, because you know what they were working on, and you know that you could have done many more things together, but today Nikos is going to show us something really cool that we got in Florida. So take it away, Nikos.
Thanks a lot, Alessio. I guess to punish me, he took me to Florida, full of alligators, ticks, and retired people, but nice ribs. So for the ribs, it was worth it totally. So yeah, we actually, I changed with this one, I guess. Yeah, so actually we went to Florida in this very nice place. It's called Apalachicola, Barrier Island Complex. And we tried to find out some more things about the last interglacial there. So as you know, coastal barrier systems, they are continuously evolving systems which we can actually observe the change in a very short time scale within years, decades, even a few days. Yet they managed to capture the interplay of sea level changes, sediment dynamics, tectonics, wave conditions, and storm impacts over thousands of years. Especially beach ridge planes, we can actually interpret them in two levels. On the horizontal plane, we can actually see changes regarding the geometry and the orientation, which can be translated in fluvial dynamics, in longshore drift and other processes. As you can see here, for example, we have the remarkable banks in Tasmania, where the changes in the orientation of the beach ridge plane can show us the change in the direction of the wave regime in the area. For example, in Brazil, we can see how the development of a coral reef more offshore of the site can actually affect the longshore drift. We can also see the effect of uplift in Baja Laura in Argentina, but we can also observe human-induced changes in these beach ridge plains, as we can see in Ombrone in Italy, where the beach ridge actually shifted 50 degrees due to the deforestation, which actually gave a lot of fluvial sediment supply in the area. So the river turned towards the incoming waves. And after, due to the damming of the river, we saw that it actually, a lot of sediments were eroded from the mouth of the river. The second one, if we cut actually a slice into the beach ridge plane, we can go directly to the vertical plane, which shows us the hidden architecture of the beach ridges, where we can actually read it, and we can see every inclined bed, every scarp, and every contact, and we can interpret it and find the story behind the evolution of the area. We can see, for example, we can interpret it in terms of sea level. We can interpret the beach dune contact and the wave berms, and we can find we can take different information from each one of the geometry of the beach faces. We can see regarding the sediment flux, how it changes with greater sediment flux. We can see a bigger distance between the beds and shorter one with the lower one. We can see how they changes in terms of wave energy, and of course we can find the traces of storm events as scarps and as deposition of heavier minerals. So to do all of this, we actually have to follow an established methodology. We have to make some GPS measurements, some precise GPS measurements. We can take advantage of the LiDAR digital elevation models. If we are lucky, we can get some nice stratigraphic profiles. And of course, where we cannot find these profiles, we can always use ground penetrating radar to reach below the surface and take an image of the vertical plane. Of course, OSL dating can also help us with the interpretation of the area. So this is the broader picture of the geology in our area. This is our survey area, but in order to understand, we decided to go a bit to zoom out from our area to understand better what is happening, because there was also a lot of controversy in the area. If we have some sea level indicators in the area, there were some sand barriers which were actually debated the origin. Some were saying that this was marine, some were saying that this is not. But based on the later data that we had from the area, we actually understood that there are a lot more than we were thinking in terms of marine deposits, such as scarps, sandbars, and a lot of other cool stuff. So when we go to our area, we can see, as you can see, there are a lot of linear features in the broader complex. But if we take a closer look, we can see that based on the LiDAR model, we can actually separate all of these units. So this is what we did. We took the LiDAR data from the area. We took advantage of all the data that were in the area. As you can see, there were already, with the white circles, some of the sediment cores which were dated. And we also collected some GPR profiles, these linear transects here, from all the units that we believed could be related to the last interglacial. So the units that you can see are categorized like this, with the green one was the Holocene beach complex. With the yellow and the orange, we interpreted it later based on the sediment cores as the early and the late last interglacial. Behind them, there were some alluvial deposits, probably from MIS6. And also there was a separate package from all of this, which we strongly believe that it was formed before the last interglacial. If we check also the sediment cores from the area, we can see what we were talking about. With this color is the pre-last interglacial. And on top of them, it was the alluvial, the transition from the MI6 to the last interglacial, and then the early and the late phase followed. The GPR profiles showed us the presence of the beach dune contact, which it was, even if it's not so easy to see it, if you interpret the data, you will see that it's detectable, and you can follow it through a big distance. What we found, one of the key findings actually, were the erosional storm scarps. As you can see here, we found a sequence of erosional features. which, based on the progradation rate of the Holocene, because we did not have any dates from the last interglacial, we actually found out that one major storm every 76 years occurred in the area, which generally agrees with the data from sediment cores from the broader area. By tracing now the beach-dune contact in all of these beach ridge units, we found that the sea level oscillated more than once in this area. And actually, if we concentrate on the early and the late MIS 5e, we can see that the sea level dropped at a rate of 14 millimeters. It dropped down to almost 2 meters, and then it raised very fast at 10 millimeters, and then dropped again with a rate of 8.7. And then again, during the late phase, as the GPR data showed us, because we had a gap after this, we had a big scarp, we saw that it raised again, and then it dropped with a much slower rhythm. All of these values, they were corrected based on the indicative meaning. The last key finding of the area is that we were trying to explain where these oscillations are coming from. So the first thing that we checked was the sediment isostasy, which was excluded since the land motion rates calculated for the last interglacial and the Holocene were too low to explain this fluctuation. So based on some modeling done by Roger, so all the experts of the GIA can actually go to Roger directly, so I'm skipping this part. These rapid changes reflect the complex global ice sheet interactions, which include the West Antarctic ice sheet collapse with the Laurentide and the Greenland melt events. And we can also find a correlation with the data from rolling in the Red Sea because the processes in the Red Sea and the Apalachicola barrier, they match by 75%. And the last one is the reconstruction of the barrier complex. We can see that initially, during the early MIS 5e high stand, we have some extensive barriers formed when the sea level rose. After that, when the sea level dropped, we had rivers which were reshaping the whole landscape. And then, during the second rise, we had some younger beach ridges actually forming. Yep, they're here. And finally, we can see that during the Holocene sea level rise, we have this landscape which we can actually observe today. So these are the conclusions. I think I have to skip it because of time, but what I would like to do is to thank these guys, Silas, Ciro, and Denovan, because I made some very good friends here. I would also like to thank Alessio for taking me to Florida. No, but apart from jokes, I think that you have established a very nice network. I remember back in the Netherlands, where we first met, and after Sardinia and after here, it was a very nice experience. Thank you.